the vast landscape of physics, two worlds often seem at odds, one ruled by Newton, the other by Schrödinger. This is where Ehrenfest's theorem steps in, not just as a mathematical result, but as a profound statement about the nature of reality. It doesn't just clarify equations, it reshapes our understanding of motion, measurement, and the very fabric of physics itself. But beyond the numbers, Ehrenfest's theorem sparks as much deeper question as one ventures into the very philosophy of physics. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to this fresh new video in understanding what is Ehrenfest's theorem. So we do with the first thing first. We start understanding what is Ehrenfest's theorem in the first part of our video. Now the Ehrenfest theorem, you can think of it acts as a bridge between quantum mechanics and classical physics. So it tells us on a whole that the average quantum particles also follow the same laws as classical objects. And the equation looks something like this. Also, it seems to be a little bit complex or intimidating, but this theorem actually gives result to a lot of important features. And what the key takeaways from the Ehrenfest theorem are this. First is that the quantum systems obey the classical average laws. So what we can understand from here is that if you measure the position or momentum of quantum particle many times over and over and again, the average result follows classical physics. The second thing which also shows is that the expectation value of the Ehrenfest theorem actually also follows Newton's equation. That means on an average, quantum particles move according to Newton's law. The third and most important is that the classical physics is an approximation of quantum mechanics. That means when quantum effects like, for example, uncertainty and wave nature are small, the system behaves just like a classical particle. And finally, Ehrenfest theorem bridges a gap between quantum and classical physics and is showing that quantum averages behave classically. So this is overall what we can understand about the easy meaning of Ehrenfest theorem. Although this is a kind of a hand-wavy easy understanding, we will take the equations one by one and understand that. But for the time being, let us understand that it acts as a bridge between classical and quantum physics. And overall, we can say the average result from the quantum part follows what are called the classical laws of physics. Now, in order to give you a better understanding, here is a kind of a pictorial understanding of the entire Ehrenfest theorem. Now, imagine you're watching this kind of a pendulum which is oscillating back and forth, which is swinging back and forth. Now, if you track the position and momentum over time, definitely you can predict where it will go using Newton's laws of motion. Now consider that if the pendulum were a tiny quantum particle and its motion would be uncertain due to quantum effects. What are the quantum effects? This motion would be affected. First of all, obviously there would be something which is called a wave-particle duality. So it says that a particle doesn't have a single definite position. Instead, it behaves like a wave spread out in space. It will also have an uncertainty principle. We cannot know both the position and momentum of the particle at the same time, the famous Heisenberg's uncertainty principle. This would also have a quantum effect which is called the Schrödinger equation, which actually tells how the system would evolve over time. And finally, the most important, quantum superposition. That means the particle can exist in multiple states at once until measured. Now, all these quantum effects taken together, what the Ehrenfest theorem says is this. It tells us that if we average out many measurements, the motion still follows Newton's law on our average. Now, this is again a very wrong notion to tell that if we average out many measurements, what do we mean by that? We will come to that part later. But what we see from here is that the oscillating pendulum, when it's converted into tiny quantum particles, and considering the quantum effects like wave-particle duality, uncertainty, Schrödinger equation, and quantum superposition, Ehrenfest theorem tells us that if we average out all those measurements, the motion still follows the Newton's law on an average. So this is a kind of a intuitive understanding of what is called the Ehrenfest theorem. However, from here what we get is that we need to understand the equations first. So first what I will do is that I will give you a fairly overall idea what those d, dt and those curly brackets etc. look over. First we start with this very familiar term. Those who have done calculus, you know what is d by dt. So what it tells that it is a rate of change of something which we will define later. We can call it as the expectation value of A, which tells how the expectation value changes over time. Don't worry, maybe these are sounding a little bit jargons to you, but eventually it will be very clear. And these curly brackets which you can see, these angular brackets, these denote what are called expectation values. We will define that. Now, as you can see, there are a lot of operators which has got a nice hat on the top, this A with little bit hat, and these are basically what are called operators. We come next to h bar, which is a familiar symbol for those who know quantum mechanics. It is called the Planck's constant, and this preamble actually comes from the Schrodinger's equation. Now, this is what is called the most important quantum operator, or the operator of quantum physics. This is called the Hamiltonian operator, and what it tells is the sum total of the kinetic and the potential energy. This is what the Hamiltonian operator tells. Now also you can see there are square brackets. There are angular brackets which are expectation values, and the square brackets are commutators. And this part, partial of the operator upon partial of t, this is also a kind of, I would say, it tells that the A explicitly depends on time, and this term accounts for the dependence. So if A does not explicitly depends on time, this term would be 0. We will come to that later. And most importantly, we see there is a commutator within the brackets, something called a A hat and a H hat. So this is what we know, let us know right for this moment, is the commutator A and the Hamiltonian B. So what it tells, it determines how A evolves under the influence of the system's total energy, which is the Hamiltonian. So all in all, what we can say technically after looking into this equation, that Ehrenfest theorem states that the time evolution of the expectation value of quantum observables follows classical equations of motion, bridging quantum and classical physics. Well, this is not a very familiar and a thing which can be easily understood. What do we mean by time evolution, quantum observables? These things we will come later. However, before we move to this part, we need to build up a framework. We need to build up 3 important basic concepts of quantum physics before we emerge into Ehrenfest theorems. And among them, the first is what is called the quantum operator. But before we understand quantum operator, here's a quick note that I also have a channel which is called General Relativity Explained, and you can go here in order to watch specific videos which are much more detailed, much more analyzed, and much more structured in lesson plan 1, 2, 3 and so on. So you can please subscribe to my channel General Relativity Explained, which is there on YouTube. So the first thing which we need to understand in order to understand Ehrenfest theorem in a better manner is what is called a quantum operator, coming up in the next part of our video. Now, if we talk of quantum operator, let us first understand that we deal with a system. It's a quantum system, and we are dealing with a very simple quantum system which has got 1 electron. Now, this is a simple quantum system with a single electron, and by quantum system, what we mean is that any physical system that follows the principles of quantum theory. What does that mean? That it would have a superposition, it would also have entanglement, and there will be definitely probabilistic outcomes. So the particle can exist in multiple states. What is superposition, entanglement, you know, and obviously quantum system is inherently probabilistic, so the outcomes will definitely be probabilistic. So we are taking a simple quantum system which has got a single electron. Now what we are denoting is X with a hat, and this is what is called a quantum operator. Don't get confused with a unit vector, because sometimes in certain books I have seen that it is written with a hat on the top, but this is what is called a quantum operator. So what is a quantum operator? It's very simple. A quantum operator is basically nothing but a mathematical rule that acts on a quantum state, which we will come to later, to give the measurable physical quantities like position, momentum, energy. So we can say that it is a mathematical rule that acts on a quantum system in order to measure something. Now, if we apply this quantum operator, which is a kind of a mathematical rule in order to measure, we apply this on our simple quantum system. What is that? It has got a single electron. Now, when we apply the quantum operator on a quantum system, we actually apply to what is called a wave function. Now hold on, if you're not aware about what wave function, I will just tell you in simple words what it is. Wave function is nothing but we call that wave function carries all the information. I would say it is a mathematical description of the quantum state. That means the wave function carries all the information that we know about the system itself. Any types of information. So we now see that a quantum operator is acting on a quantum system. And that quantum system is basically defined by a wave function. What is a wave function? It is a mathematical description of whatever we want to know about the quantum state. Now, and also we should note that this wave function, which is denoted by the Greek letter psi, is something that is directly related to the probability distribution of the system. Now, again, you might question, what is the probability distribution? It is something which gives us a likelihood to find the electron in a certain region in space. So, for example, we find the electron either here, or there's a high probability which is marked by the red arrow. We have a high likelihood that can find the electron over here. So it gives us nothing but the likelihood, remember, not certain, to find the electron in this case at a certain area or a region. Here we are making the measurement of the position of the electron. So technically, I would say that a probability distribution actually describes how likely different outcomes are in a random process. And the probability distribution is given by the square of the wave function's magnitude, which is simple as psi x to the power 2, that is squared, and this px is nothing but it is called as a probability of the position x. So what we understand is that from a quantum system which has got all the quantum properties, the x operator or the quantum operator is trying to measure something, and when it is acting on a wave function which carries all the mathematical description of our system, it only gives a probability distribution or a likelihood where the particles can be found. And this is what exactly it is. Now, this operator, as we know, that it is applied to what is called a wave function, and it is written something like this. Now, say for example, what do we mean physically? This is actually, it is meaning that we are making a measurement. Just in case of classical physics, here also we are making a measurement. So the operator here, you can see that every time you see the operator applied to a wave function, just remember that you are making a measurement to the quantum system, just in classical physics, the way we do. Now, when I'm saying that x with a vertical bar with a psi, these are actually notations of Bra and Ket. I'm not going into that. The operator is labeled as x. That means as x position along the x-axis with a nice little hat on the top, which denotes to be an operator. So that is how if we find it. So we are applying the position operator to a wave function. Now, in classical mechanics, it is very easy to make a measurement. Now, say for example, this is a kind of a nice ball, and how do we measure? We just pull out a stick and a ruler and we find out whether it is at position 2 or 3 and so on. But making a measurement in quantum system is not that easy. So what we can do it now is that when we do a measurement, the ball can be either here or here or here. And that is the difference between classical measurement and quantum measurement. So what we can do now, how can we find out? We can find out using a probability distribution. So probability distribution, in this kind of a distribution, it shows that it is a fair chance, a likelihood to find the position of the electron or the subatomic particle in this part of the space. Now, note that it does not appear to be a position, but to other things which we will shortly see. Now, the question is that we all understand that classical measurement is a precise definition. Quantum measurement gives only a probability distribution. The question is that what actually happens when we make the measurement? And there's something really weird things which are happening. Let us look now in the next part of the video that when we do the measurement, what happens? So when we do the measurement, so there are two scenarios. One is before the measurement and another is after the measurement. So before the measurement, the probability distribution curve is this one, blue one, where we know that there is less chance to find the electron here, here, and here, and a high chance to find over here. But the moment we do the measurement, it causes a fundamental change in our wave function, and which is called the collapse of the wave function. And we know 100% that the electron is over here. So as you can see, the wave function has changed because the entire probability distribution has changed. So making a measurement, remember, in quantum mechanics has a serious implication and consequence on the system, which is not in a classical system. Now, note that it is not that the electron actually collapses. What happens, it is that the wave function collapses and the entire probability distribution changes. So here we know that after the collapse of the wave function, here is where the electron would be. And remember that this also is not that we keep on measuring that the electron is here for a quite certain amount of time. You will see that the location of this electron slowly changes and the probability distribution actually spreads out. So for a certain very, very small sliver moment of time, we can get the probability distribution, but the spreading of the probability distribution is also actually happens, and we become less and less and less sure about the position as time passes by. But Erwin Schrödinger has defined a wonderful equation which is called the Schrödinger equation, and this Schrödinger equation actually tells that how the probability distribution or the quantum system evolves over time. So that is how it is, and here you can see that it tells that the wave function evolves over time. Now the beautiful thing is that you already see that there is a Hamiltonian operator also which is acting on a wave function. So from here we are slowly getting an understanding of what is quantum operator, what happens when we make the measurement, and the wave function collapses. Now, the another important thing about is that there are certain operators apart from the position operator that is also worth mentioning. The first one is the position operator, which we have already seen, and it carries a nice hat on the top. So what it does, it simply multiplies the wave function x. So we get x psi x equal to x psi of x. And this means that it is just a scaling factor of x. Another operator is there which is called the momentum operator. And in the position representation, momentum operator is just a differential operator, and it looks like this. And acting on a wave function, it yields this. The next big boy of quantum mechanics, so you can see here that this tells us how the wave function changes with position, linking the momentum to the shape of psi x. Now the big important part of quantum mechanics is the Hamiltonian operator, and you have just seen that it also happens in the Schrödinger equation. So the Hamiltonian operator gives the energy, and what we can see over here is that the Hamiltonian gives the total energy, and acting on the wave function psi x, it also yields to the Schrödinger equation. So this is the Schrödinger equation which determines how the quantum system evolves. We just seen that the probability immediately spreads out, and it becomes very difficult for us to pinpoint where the electron is all about. Now here I would like to talk about a very important concept, kind of a misconception, that when we talk of making a measurement, it is not that a conscious human being or a conscious being is present that is making all the difference. It is actually the interaction in our system that measures and that makes the difference. So the question lies is there a conscious being which actually causes the collapse? And this brings us to the next part of our very important understanding, is what is called a wave function collapse. And this is a very common misconception among students and those who are just started to learn quantum physics. Now, there's a common misunderstanding which is influenced by the Copenhagen interpretation of quantum mechanics, that there is a continuous observer who plays a role in the collapse of the wave function. So these two images are the same one. It actually denotes the wave function. So now you can see that this is the common misconception, that there is a conscious observer, conscious player who is responsible for the wave function. Now the idea which arose due to the difficulty is which constitutes the measurement in quantum mechanics, and this is what is called the decoherence, and the collapse of the wave function actually happens due to what is called quantum decoherence. These are not jargons, I'm just explaining you in very simple language now what is a quantum decoherence. Now, in the quantum decoherence, this is the process by which a quantum system loses its quantumness. Now, this is, I understand, is a wrong English, but what I'm trying to understand is that the nature of quantum mechanics, position, superposition, uncertainty, that is called quantumness. And it starts behaving more like a classical system when the decoherence actually occur. Now, I want you to imagine something like this. Imagine this is a spinning coin, and before you look at it, it is in a superposition of both heads and tails. Now here is a rippling water, a pond or something, and if the coin falls into the water, interacting with the environment, it ripples, makes it settle to either heads or tails. And this is what is called the quantum decoherence. If the coin falls into water, and after interacting with the environment, whatever the environment it is, air, moisture, whatever, the ripples makes it settle to either heads or tails. So this is how quantum decoherence happens. So from here we get a clear and a nice definition of quantum decoherence. We say that quantum decoherence are like those ripples, and it forces the system to lose its quantum weirdness, that is those superposition and wave function, etc. And it starts behaving classically. That means we see only either the head and the tails. Now, as we use these English words, decoherence comes from the word coherence, which means logical and consistent. And decoherence is something which is illogical, not consistent. Let us take a simple word. Say, for example, if we say the team's initial coherence and shared vision were strong, but disagreements over strategy led to decoherence and a breakdown of communication. This is a simple understanding of what is called a coherence and a decoherence. Here also, the quantum decoherence makes it illogical, and we measure something as behaving classically. Now, if we get this kind of a quantum system, it exists in a kind of a superposition of states, which is mathematically denoted as this. Here you can see there's this psi is the quantum state, psi1 and psi2 are possible states, and C1 and C2 are probability amplitudes, which are basically complex numbers. We are not going into that. Now, the probability of measuring is actually guided by Bond's rule. You can go to my other videos in the mathematics of quantum mechanics, where I have stated how squaring this it would give to. Now, when the system, now let us say this is a quantum system, and it starts interacting with macroscopic device. For example, it can be a detector, it can be molecules, etc. So say, for example, these brown dots are basically detectors or environment or anything you can imagine. The delicate quantum superposition is destroyed, and it is detected by interaction with the environment. So this is, after the detection, this is called quantum decoherence, where the system becomes entangled with the measurement apparatus. So here is what we call, when the system interacts with macroscopic measuring particles, detectors, whatsoever, the delicate quantum superposition is destroyed, and by the interactions with the environment, and that causes what is called the wave function collapse. So we can now understand that it has nothing to deal with conscious being, or the scientists make a lot of philosophical interpretation of that. It is basically caused by the quantum decoherence and by the interaction of the particles. So the quantum system, if you take this one, the quantum system around tiny particles like airs, molecules, photons, or measuring instruments, this is what is causing the influence. So the moment we start measuring it, it causes a wave function collapse, and this wave function collapse gives the probability outcomes, and the Bond's rule helps us to measure them. So from here what we can say is that the wave function collapse into either of these possible states. Number one is this one, that when we measure this, it gets into either psi1 or psi2 with probability C1 and C square respectively. And if the system interacts with the environment, not I would say exactly measured by the observer, it becomes entangled with the environment, which is mathematically shown as this, and these are environment states E1 and E2. So what happens essentially is that the system chooses a definite state, and the quantum effects disappear, and now it actually behaves like a classical object following everyday physics. So before measurement, quantum superposition exists. Measurement or decoherence destroys superposition and causes the system to take a deliberate state, and mathematically this is described using projection operators and the density matrix formulation, which we are skipping for this part of the video. So here is a quick summary of what we have understood, that the collapse of the wave function is definitely not caused, is caused by the quantum measurement of the measuring device, and there is no need for a conscious observer in order to do that kind of an understanding. So there is absolutely no presence of conscious observer. It is basically the decoherence which causes the collapse. So far so good. Now what we also understand from here, that if you take a quantum system, we have just seen that it takes a measurement and the wave function collapse. But in case that we are doing a measurement which causes a fundamental change of the system, what if we make two measurements instead of one? So making two measurements are more complicated. Why? Because here the order in which you make the measurement, this one or whatsoever, actually matters. And this brings us to the next important building block of understanding Ehrenfest theorem, is called the commutator. And this is very important. We have to build up three bases. One, we have already understood what is a quantum operator. Now we are going to understand what is a commutator. Coming up in the next part of the video, we'll understand that what is a commutator in very simple mathematical terms and language. Now in classical physics, if we try to measure the position and the momentum over a certain time, it doesn't change. That means the order in which we measure them, for example, position or momentum or any value, it really doesn't change. For example, if we take x equals to 5 and p equals to 10, for example, x is the position and p is the momentum. And if we swap the order, then x times p will be equals to p times x. So the result here would be 5 times 10, which will be equal to 10 times 5. Now this is actually which makes a little bit of difference in terms of quantum system. Now as you see here, the results are identical regardless of the order, and that is why in classical physics position and momentum commute mathematically as xp equals to px, and that is why we don't have any uncertainty principle or collapse of wave function. Now measuring the position of the quantum system changes the wave function. So when we measure the wave function, the collapse of the wave function which happens after this, then what happens is that the order really matters. So measuring the position of the quantum system changes the wave function. So when we measure the momentum afterwards, we are actually making the measurement in a totally different wave function. So here you can see what I'm trying to say is that psi px psi is not equal to xp psi, where x is the position, p is the momentum, and these are quantum operators. And this is what actually makes a huge change in terms of quantum and classical physics. So you see the wave function has collapsed, and we are making the measurement after the collapse of the wave function. Just as in classical physics, here when we make the measurement, it is px psi is not the same as finding the momentum first and then the position. And in quantum physics, in classical quantum physics, this is not equal to this, whereas in classical physics, obviously xp will be equal to px. So what we will come to the commutator part later. So what we are assuming that measuring the momentum afterwards, we are making the measurement of a different wave function. Coming to this part later, we will also take into account this thing. So here you can see if we measure the position first, x, and then the momentum next, p, can give you a different result when you're measuring the momentum first, p, and the position second, that is x. This is a difference. So here I have written it in simple language. Measuring the position first and then the momentum can give us different result when measuring the momentum first and of the position. But remember, typically in case of classical physics, it really doesn't happen. And now in order to know which operation is done first, we can see the one which is very nearest to the wave function. So on the left hand side of the equation, you can see that the operation which is done first is the position, because beside psi comes the x. On the right hand side, besides psi, the immediate part is p. That means the first operation, the first measurement is done with the momentum, that is p. So xp, obviously we know that when it is not equal to this, that means subtracting would also not give us 0. Whereas in case of classical physics, 3 times 5 minus 5 times 3 would equal to 0, because 15 minus 15 would be 0. So as psi x, this one, xp psi is not equal to px psi, that means subtracting would also not give us 0, which classical physics is different. So now if we try to factorize, I mean to say not the algebraic factorization, what I'm trying to do is that I'm trying to make this wave function psi out of the bracket. We get something like this. Don't worry, this something is not which we are really worried about. What we get is that this xp minus px is something kind which we call as a commutator. Now a commutator something is when we get something like this, and commutators are written in square brackets around with the quantities. So commutators actually tell us the order in which we make the measurement actually matters. So here you can see first we are making the position, and then the momentum, again minus the momentum, and then the position. So as we see that commutators are written in square brackets, here with position and momentum, it does matter as it is not equal to 0. Now this one equals to IH bar. This is the fundamental commutator relation in quantum mechanics. Let us assume that it is. And what is important is that x and p do not commute. That means the order in which they are measured do matter. So when they are not commuting, when it is not equal to 0, that means that the order in which it happens actually do matter. Now, in case we take another kind of a scenario, so I have written this but, that means what is our other way around? Here we have seen they do not commute, so the order do matter. But let us take another scenario. Let us take an equation something like this. So measuring O first here, measuring O first and then P gives the same result because it is equal to measuring O first and then P gives the same result by measuring P first and then O. In that case, the commutator would be 0. So as you see, I've written the commutator would be 0. So obviously when it is equal to 0, performing a subtraction would be also equal to 0, and also the commutator. So that is how actually things happen. So from here, what we can get is there that these people do not commute. So x here, you can see that the order in which they are measured do not matter. Why it doesn't matter? Because it is all equal to 0. Now this one, so OP equals to PO, and it is something which is similar to this one, 9 times 2 equals to 2 times 9. Now commutators are very important in quantum mechanics. So we understood one commutator where it doesn't commute and it is not equal to 0, and when it do commute, it is equal to 0, and that is why we say multiplication is commutative. But commutators, we are learning why, not only for the Ehrenfest theorem, but it is important in quantum mechanics, because here you can see this measures these two operators commute. So x, the position operator, which acts on a wave function with given position x, and px, the momentum operator in quantum mechanics, is given by this one. And most importantly, I would say since the commutator is not 0, it tells us that position and momentum cannot be measured simultaneously, which actually leads to the famous Heisenberg's uncertainty principle. This means that one precisely increases the uncertainty of the other. So since the commutator is not 0, it tells us that the position and momentum cannot be measured simultaneously with absolute precision. Although this is not one of the reasons of uncertainty principle, there are other reasons, but this is one because they actually do not commute. So they actually leads to no precision understanding. So this is one part where commutators play an important role. We can also look the commutators in case of matrix operation. So for example, we get a matrix A and B like this. We take a product of AB and BA. So here you can see that AB equals to BA. So what it tells that these matrices do commute. And if we take the non-commuting example, for example, this matrix, we take a product and then we actually do the subtraction. Here you can see that it is not 0 because the matrices do not commute. Just it is a similar example that position and momentum in quantum mechanics do not commute. So this is example with matrices. Well, we will now take a pause and let us quickly summarize till now what we have learned so that we can now move to the true part of the Ehrenfest theorem. So what we have understood till now is this one, that if you get the commutator is equal to 0, order of measurement does not matter. And if it is not equal to 0, then order of measurement really matters. We have also seen that classical mechanics, the order of measuring position and momentum doesn't matter, whereas in case of a commutator, it helps us to determine whether the outcomes or what is the way we measure. We have also seen that the Heisenberg's uncertainty principle arises as one of the reasons of the non-commutative property of quantum operators, and commuting operators also allow simultaneous precise measurement, and in quantum mechanics, if two observables do not commute, measuring them in different orders leads to different results. So we have understood what is a quantum operator. We have also understood what are commutators. And we are now left with the last part of one building block, that is what are called expectation values. And using this, we will go into what is called the Ehrenfest theorem. So if you're studying the wave function, now say for example, this is a quantum system again. For simplicity, I have taken a single electron. And if you're studying that, the wave function, it is applied to the wave function, which gives a kind of a probability distribution, something like this. And the probability distribution says that the electron has less chance of finding here, here, or here. And this is just telling us the likelihood of finding electron. Now, because quantum mechanics is probabilistic inherently in nature, then how do we do a kind of a measurement? And this is where the expectation value comes in. And the expectation value is nothing but it represents the average outcome of measurements if the same experiment is repeated many times. So we can say it helps in calculation by providing a way to determine observable quantities like position, momentum, and so on. So expectation value is equal to, we can say, a weighted average of a probability distribution. Now, if you again take this kind of a probability distribution, it is most likely that the electron would be found around this and less to be found around other radius. So in this case, the probability distribution is very symmetric, and hence the expected value is just what we call is the average position. But here is a point of caution, that expectation value is not always the most likely where the electrons can be found, because expectation values are actually not the average, but we can say it is of equal to mean value. Now, in order to do that, I will take you through a very simple example so that you can understand that it is not always the most likely to be found. Now let us take a kind of a probability distribution like this and this. So it goes up and down. So if you get a probability distribution like this, then we cannot find the electron here or here, isn't it? So the expectation value is where? It is over here. So expectation value is not always the likelihood of finding the electron, but rather, but here you will see that there is no chance of finding the electron over here. So that is why the expectation value, it shows that is not always the likelihood of finding the electron here. Rather, so we write this in this way, the expectation value is not always to find the electron, that it is weighted average. So this is how we actually write how an expectation value looks like. All these angular brackets determine what are the expectation values and the value it is within it. However, in quantum mechanics, it would be incorrect to like this. We should write like this. This one is basically the bra, the complex conjugate of the wave function. This A is the quantum operator corresponding to a physical observable, and this part is the ket representing the wave function. So now the question is that we have seen that expectation values is not where we can most likely find the electron. Then why do we understand expectation values? Why do we need expectation values at all? And the answer is that in quantum mechanics, there can be fluctuations due to the uncertainty principle, and the expectation values actually closely resembles Newton's law, especially when quantum fluctuations are small. So expectation value can lead to a lot of good calculations, and it actually gives a meaningful understanding of Ehrenfest theorem, because it will give you a better understanding that classically how these values actually perform, and this will become much better in the next part of our video. So with all those equipments and the tools under our belt, we go ahead in the last part of our video and we now understand what is an Ehrenfest theorem. So a quick review, what we have understand that these are little hats, these are position, momentum and Hamiltonian operators. We have also seen what are position, momentum within square brackets, these are commutators, and the angular brackets are the expectation values. So with that we go directly into understanding and decoding this. This is basically the Ehrenfest theorem and the equation as it looks like. Now, first of all, we will see that we have already understood these parts. A, what are those? These are just operators. And we have seen the square brackets. What are those? These are commutators. We have seen the angular brackets. What are those? These are expectation values. And what is most important is this important part, the H, the big part, that is the kinetic energy plus the potential energy, which gives actually the total energy of the system. Now you might be wondering, there are so many A's, 1, 2, 3 A's. What are A's? A's are nothing but they are just placeholders. They are just generic operator, and we will soon see that these can be substituted with other values, yielding to a great, wonderful, magical results. Now what we do is that we are going to substitute the position operator, that is the x hat, on this A, and the equation turns like this. We could have also substituted the momentum operator p hat in the Ehrenfest theorem, and we get something like this. Now by substituting, what happens is this one, that when we substitute different operators, we see that Ehrenfest theorem, we get a quantum equation that resembles something like classical mechanics on an average. And this is where the classical and the quantum physics actually result into the bridge there. Let us look a little bit more details in this. So we have understood what are A's. Now we come to this part, which is called the d by dt of A. So what does it represent actually? Now this represents the time derivative of the expectation operator A, and we will soon replace that with the position operator x. And it physically tells how the average position of a quantum particle changes over time. And what is this one? We are not going to deal with the partial derivative part, but we can understood from first part is that d by dt means how much the quantity changes with respect to time. Here we are finding the rate of change with respect to time of the expectation value A. Now these curly d's are actually what are denoting the partial derivatives. So what it says is that this represents the explicit time dependence of x. However, in most cases like free particles, the position operator does not explicitly depend. So you can understand this is rate of change of the operator A with respect to time and the expectation value because of the curly brackets. And this term represents the explicit time dependence of the operator A. And for you, with your surprise, you will now see that this part actually vanishes. So when we talk of the operator x and p, we are trying to tell that the position and the momentum operator actually do not change with time. This is important because operators, remember, they correspond in making measurement. And what is important is that how we make the measurement, either position or momentum, does not change with time. It might yield to a different result, but how we make the measurement does not change in time. So if an operator itself changes with time, it has got explicit time difference. If an operator remains the same at all time, then its partial derivative with respect to time would be 0. So when we say operators that do not explicitly depend on time, we mean to say that if an operator itself changes with time directly, it has explicit time difference, and if it is not, then its partial derivative with respect to time becomes 0. And this is a very good news for us, because here x simply represents the position of space. So partial of x with respect to time would be equal to 0. And that actually makes a lot of our Ehrenfest theorem equation fairly easy to understand. So here you see that we next come with what is called the momentum operator. Now the momentum operator only involves what is called the differentiation with respect to space and not with time. So again, partial differential of the momentum operator with respect to t again would be 0, and partial of x of partial of t would be 0, and the expectation of value of 0 is 0. So this actually solves a lot of problem, and only with which you are left is 1 upon I h bar. As you know, these are constants, so I is square root of -1, which shows that quantum physics deal with complex variables, and h is the Planck's constant. So it is just a scaling factor in quantum mechanics. For the sake of this video, let us understand that this is just a constant. So what we are interested is the expectation value of the commutator between a and h. So what we now will do, so this is what is important, the expectation value of the commutator between a and h. And now what we will do is that we are substituting a for the position operator, and we see the end result. So it turns out to be here. Now here is a quick note. If you really want to skip this part of the video, you can, and you can go to the calculation part where the final results come up. So for calculations, you can look the end result. However, I would recommend that to have a look at this very simple calculation. But if you want, definitely you can skip this part, because what I'm going to do is that I'm going to show you in 3-4 simple steps that how we recover to Newton's laws of motion. So when we put the operator x in the area of a, that we substitute the value of x for the operator a, what happens is this. Number one, we take the Ehrenfest theorem, which we know as this. Now we substitute a for x, and what we get is this one. And the term, this part, is usually 0, because the position operator, as we have seen, does not explicitly depend on time. So if it cancels out here, it's a red cross, so it cancels out, we are left only with this part. So we go to the step 3 and we evaluate the commutator, and by evaluating the commutator, you can pause the video and you can look in the calculation. We get something like this. Now here is something which we call, there is a catch, and the catch is that here x represents the position operator in quantum mechanics, and the Vx represents the potential energy of the system, which obviously depends on the position x. So the two operators a and b commute, and if their commutation operation is 0, then it looks something like this. So now we say that since Vx is just a function of x, it means that multiplying Vx actually does not change the order of the calculation. So mathematically, it looks like this. And this is the good news of us. Again, I repeat, since Vx, which is representing the potential energy of the system, is just a function of x, it means that multiplying by Vx does not change the order of multiplication, and we get this expanded value as 0. And this happens because both built on the same operator x, so they act in the same way. So what does this mean for Ehrenfest theorem? So it means that in Ehrenfest theorem, we need to compute the commutator x and h. And since the Hamiltonian contains the potential energy Vx, the commutator x is much more simplified. That means, if you take an analogy, that if you say, for example, if you have a number like 5 and a function of that number, for example, like squaring it to get to 25, so multiplication does not care about the order when dealing with just these numbers, because 5 times 5 square is equal to 5 square times 5. So since Vx here is just a function of x, they do not interfere with each other when it is multiplied in quantum mechanics. It's just an analogy that 5 times 5 square is equal to 5 square times 5, because this is a function, and here also potential energy is a function, so it would commute, and the commutator x becomes much more simplified. So we are left with this one, because this is already a function we have seen. So in the step 3 part, what we do is that we evaluate the commutator, this part, and we cancel out Vx. Why? We have seen the reason, since Vx is a function, or we can say x commutes with Vx, and we only need to compute this part. So using the fundamental operator we have seen in the first part of the video, we expand this part and we get this, and this and this. Now these are just calculations. As I told you, you really don't need to look into this, but these actually results into something very important. Now, so from here, this part, we get these values. We are now substituting back these values into Ehrenfest theorem. And when we substitute values, we get something like this, which equals to this and which equals to this. Now this one, which I have just highlighted in a red box, this is important. Now why this is important is that what it tells actually is this one. When we get, so this one you can see now it is equal to the classical momentum part. So what we get after all those step 1, step 2 and for 4 steps calculation is that what we get is that the rate of change of the expectation value of the position of our electron, the rate of change of the expectation value of the position of our electron multiplied by the mass of the electron, which is the m, multiplied by mass m of the electron, is equal to its expectation value of its momentum. Let me repeat once more. So from this calculation, we are actually getting two values. Either way, I've just put this m at the denominator and the rest is the same. So these are two forms. So what we again get is that the rate of change, this one d by dt, of the expectation value, which is in this curly brackets, the rate of change of the expectation value of the position of the electron, which is this x hat, multiplied by the mass of the electron, which is m, is equal, this one equal to its expectation value of its momentum. And this is exactly what happens in classical mechanics, where velocity is momentum divided by mass. Now, in order to demonstrate that, I would just like to take a quick glance back and let us imagine this ball is moving in this direction. And the rate of change of the position of this ball with respect to time is simple dx by dt, which is equals to velocity. And when we multiplied m dx by dt, we get what? mv. And p equals to mv, that is the momentum. So the rate of the change of position of ball with respect to time is the same thing as its velocity. When we multiply it by mass, we find its momentum. Now in the Ehrenfest theorem, what we could do is that here comes the linking factor. Now in classical physics, we got the momentum part, and now you see in Ehrenfest theorem, it is the same. In the Ehrenfest theorem, we deal what is called the expectation values, where in classical physics, we already know for specifically this is the position and the momentum. But the good part is that although quantum physics is weird and probabilistic, when you look at the expectation values, it actually behaves almost like classical physics. Though the probability distribution changes something like this up and down, doesn't matter. But what Ehrenfest theorem tells is that if you look at expectation values, they behave almost like classical physics. So here also we get a momentum, here also the mass of the electron, here also you get the mass of the ball. And if you look at the expectation values, they behave almost like classical physics. So the understanding is that when we talk of the ball, we are talking of the change with respect to time is the velocity, and multiplying by mass, we get the momentum. Same in Ehrenfest theorem, we deal with expectation values, but here it is because quantum system we deals with expectation values. Here also it is the same. With respect to time is the same change in velocity. When it is multiplied by the mass of the electron, we find its momentum, but it is in terms of the expectation values. So from here we can say that the average or the expectation value of their position and momentum obeys the classical equations of motion, and that is why I call that Ehrenfest theorem gives a very deep insight and acts as a bridge between classical and quantum physics. So from here what we can tell is, number one, individual quantum particles, although they behave probabilistically, the average expectation value of their position and momentum obeys classical equations of motion. And this means that there is a very smooth transition into classical mechanics. And Ehrenfest theorem shows this one, which is exactly how classical velocity or classical mechanics relates to the momentum. Now, it is not only that we substitute position, but we could also substitute momentum in the place of A. As I told, A is nothing but in generic a placeholder. And when we do that, the Ehrenfest theorems look something like this, and this exactly matches with Newton's second law, which means that the expectation value of momentum changes according to the classical force or the classical mechanics. So we come to the end of the video where the Ehrenfest theorem actually tells that like the position, Ehrenfest theorems, if you substitute the momentum, also leads directly to Newton's classical law on average. And by substituting momentum into Ehrenfest theorem, we recover Newton's second law. And this confirms that on average, quantum systems obey classical physics when looking at their macroscopic behavior. I leave you with this picture, and I hope you can recognize in these 1, 2, 3, 4, 5 great physicists who is Ehrenfest in this, Paul Ehrenfest in this picture. If you know, please put up a comment who and where is he standing. And apart from Albert Einstein in this picture and Ehrenfest, there are 3 leading physicists who are standing and sitting. If you can recognize them, please let me know in the comment box. That's all for today's video, and we complete the Ehrenfest theorems learning. Thank you very much for watching this video. If you have liked, please do not forget to click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. And I have started putting up good videos and regular videos on my channel General Relativity Explained, and you can watch this video for enjoying general theory of relativity, and you can contact me at this ID. Physics for Students will keep you surprising with this type of fun physics and loving videos, but till then, goodbye.